This is a problem that concerns a physical situation I've actually seen, okay? So I've been in situations where I've been in a sculpture park and we have sculptures hanging from cables. And I'm going to do a little abstract sculpture here. And then when the wind blows, the wire vibrates. And when I've heard this happen, it's a pretty low pitch, okay? But it's going to vibrate. Now think about this. This end up here is fixed, okay? This end is connected to the sculpture, so this end is fixed. And so what I have basically is standing waves of a wire which is fixed at both ends. And so the frequency of the hum, what we mean is this. We mean the fundamental frequency. I'm looking for F1, the frequency of the M equals 1 standing wave mode, because it's fixed at both ends. And if I'm looking for M equals 1, I'm looking for the lowest possible standing wave mode frequency. It's just this. F1 is equal to 1 times V over 2L. That'll be the frequency of the hum. Now you'll get the other harmonics as well, but this will be the pitch that you perceive the hum at, okay? It'll be that frequency, just V over 2L. Now L is the length of the wire, which is known. So really, what this problem reduces to is finding V. What is V equal to? Well, the V is the speed of the wave on the wire. And remember, in the previous chapter, we saw that the speed of the wave on a stretched string or a stretched wire is equal to the square root of T over mu. Now, mu is equal to M over L. That's the mass of the wire divided by the length of the wire. Well, both of those are given in this problem. It's a 5-gram steel wire, so it's 0.0050 kilograms, divided by the length, 90 centimeters, 0.90 meters. And so the mass per length of this wire is just 0.00556 kilograms per meter. Now notice I'm keeping an extra significant figure here because this is an intermediate stage of the calculation. How about the tension? What is the tension equal to? Well, let's draw a free body diagram for the sculpture. Okay, the sculpture has got two forces that act on it. It's got the weight force, okay, which is just equal to M times G as always, and it's got an upward tension force. And it's a hanging sculpture. It's not accelerating vertically. So we can say the tension force is just equal to the weight force. That's just equal to M times G. The mass is known. It's a 12 kilogram sculpture. And so the tension is just equal to the weight, and that's just equal to 118 newtons. So we have the tension, we've got the mass per length, we know which standing wave mode we're looking for, we're ready to do some solving. And here's what we get. The speed of the wave is equal to the square root of T over mu. Now we calculated both T and mu here, and if we take those numbers and substitute them, we get 146 meters per second. And that's pretty zippy, okay? That's pretty zippy, but it's a relatively lightweight wire. It's 5 grams of wire, and it's got a pretty significant force on it. It's hanging a 25-pound weight from it, so this is not unreasonable. The frequency of the lowest standing wave mode is just equal to 1 times V over 2L. V is equal to 146 meters per second. L is the length of the wire. That's 90 centimeters, 0.90 meters, and so as a consequence, I end up with the frequency of this particular mode of 81 hertz. So this is just a classic standing wave on a stretched cable, on a stretched wire, on a stretched string problem, kind of in disguise. Is this reasonable? Well, in my experience, yes, these numbers are reasonable for the sculpture and for the wire. And when I've heard this happen, the frequencies that you hear are kind of like very, very low. It's kind of an otherworldly sort of experience. And so this matches, at least my experience, of how the world works.